Morning to one and all present here. So today we are going to see about the bus admittance matrix, the formulation of bus admittance matrix and the problems. So if you see the interconnected power system represents an electric network with multitude of branches and nodes. Okay, so multitude of branches and nodes where the transmission line, okay, where the transmission line constitutes the branches. And at some of the buses, at some of the bus power is being injected to the network, whereas other bus it is being tapped by the system nodes. Say, for example, bus admittance Y and bus impedance Z are two important network matrices. Okay, as I said before, two important network matrices which find applications in many power system planning and operational planning studies. Say, for example, if you are going for Gauss-Seidel method or Newton-Raphson method, the first step is the formulation of Ybus matrix or Z matrix, depends on the problem. Okay, whatever given and whatever we are going to calculate. The very first step is formulation of admittance matrix or impedance matrix. So that's why this particular topic, okay, has some importance. Okay, next step. The injected bus current and bus voltage of the bus system under steady state conditions. Say, for example, how you can relate, it's this relation already. So Y into V is equal to I. Okay, so V is equal to IR. Okay, so IR is nothing but say, for example, V is equal to I into Z. Z, okay, impedance is Z. So if you come with okay, so B is equal to I into 1 by Y. Okay, Z, or in the other terms, I is equal to Y. So these are the two important formations. Next, formation of Ybus matrix by two-rule method or inspection method. Okay, inspection method or two-rule method. Okay, so consider the three-bus power system. So three-bus power system, but practically speaking, if you take practically, there are many buses. There are many buses in the system. So for easy analysis, we are taking only three bus. Okay, three bus, and we are having having two generators. And here from bus 1 to 2, that is a connection, and 1 to 3, that is a long line. So 1 to 2 is a short line. As I said before, if you take like any generating station, like a thermal generating station, okay, or hydro power generating station. So here you can find the generators nearby. Nearby means a very short distance might be the generators. And if you take the transmission lines, say for example, 1 to 3 long line, say for example, some 100 kilometers or 200 kilometers, depends on the where the generating station is situated from the load. And here you are having the shunt compensation like. So this three bus sample system is being given in the problem. So equivalent, we are converting this three bus system into equivalent power network. So what we are doing here, equivalent power network, say for example, Y is nothing but admittance. Y dash is nothing but offline charging admittance, and Y is nothing but admittance represented for the load. Okay, in the equivalent circuit shown in the 3.2, okay, the 3.2, that is equivalent circuit, generators are replaced by Norton equivalence. That is, load is replaced by the equivalent admittance, and the line is replaced by the pi equivalent circuits. Okay, so this already you studied this concepts in your generation, transmission, distribution, or power system 2. Okay, so it depends on the syllabus. Okay, in some university it is generation, transmission, distribution. In some universities it is power system 2. Okay, so here you already framed this pi equivalent circuits and all. So the admittance of the generators, loads, and transmission lines are given in the per unit. So what we are doing is we are converting this sample bus system, 3-bus system into Norton equivalent circuit for the generators and others. Okay, so and others, what we are doing is load is the equivalent admittance and the line is replaced by the pi equivalent circuits. Okay, so here what we are doing is we are converting this generator into current source. Okay, and also we are in the generators we are having the admittance of the generators also. Okay, and here short line we are converting into Y12. That is some admittance between this bus 1 and bus 2. Okay, like and here here 1, 2, 3 we are having some admittance as Y13 and Y here we are having 2 Y13 dash Y1. This is what Y13 dash is nothing but offline charging admittance. Okay, so that is offline charging admittance. Y dash is nothing but so here Y13 is a offline charging admittance between the bus 1 and 3. And here also Y23 dash is nothing but Y23 dash 2 Y23 dash. So between 2 and 3, bus 2 and 3. So it is nothing but half line charging admittance between the Y2 and 3. And here 3 and okay ground. So that we are taking as Y3 not. Okay, and between Y2 and 3 you are having Y23. Okay, admittance as Y23. So this is how we need to create the equivalent circuit. So and YD3 what that is nothing but load. Okay, load admittance. We are mentioning it as YD3. So that is here admittance represented for the load is nothing but YD. So load admittance we are so this is the load bus. The third bus is the load bus, and this 1 and 2 are the generator bus. So that you need to develop. So whatever the power system given in the problem, so you need to convert and write. Okay, if not some in the problems itself, sometimes it will be given. But the thing is that you know this formulation, how to convert the sample bus system into equivalent bus system. That understanding is very, very important for you. Okay. So next what we are doing is the admittance and the admittance of generators, load and transmission lines are given in the per unit. The ground is taken as a reference node. So ground is here, the ground is taken as a reference node. So applying the Kirchhoff's current law to the node 1, 2, and 3. So what we are doing is we are applying the Kirchhoff's current law at node 1, 2, and 3. Okay, so node 1, if you apply the Kirchhoff's law, it is nothing but YG1 into V1. So this is the current law. So equivalent, so current. So from this formulation, current Y into V. Okay, so Y into V that we need to create. So Y into YG1 into V1 plus here Y12 into here what is V1 minus V2. Okay, Y1 minus V2. Similarly, Y13. So what are all the things connected in the node 1? Say for example, so this is the generator admittance is connected. That is self admittance of generator and Y12, Y13. Y13 what? So Y13 into okay V1. V1 minus V3. Okay, V1 minus V3. And here self here Y offline charging admittance that also you need to take. So that is Y13 dash into V. So that is nothing but I. Okay, understood? No. So this is very, very important for us. Okay, this whatever the things given to you, whatever the problems given to you, not only like this, whatever the problems given to you, you need to formulate. You need to formulate like this kind of current law. Okay, so say for example, if the in the problem it is given as impedance, then what you will do? The same formula. So here B is equal to I into Z, or otherwise I is equal to B into 1 by Z. So here the same thing. Say for example, if it is given in impedance, you need to take 1 by Z. That's all. Okay, same thing 1 by Z. So that you need to very careful while doing the calculation, whether it is admittance or impedance, that you need to identify, and based on that you need to solve. So for the simplification, what we are doing is, so we are taking all the so V1, we are taking V1 because all here V1 is there, and after that we are further simplifying, that is V1 into YG1 plus Y12 Y13 plus Y13 dash. See, these are basic mathematics. Then minus B2 we are taking out. So B2 only one B2 is that okay, B2 into Y12 and B3 into Y13, that is equal to I. Similarly for node 2, what node 2 here YG2 into B2, okay, YG2 into B2 plus Y12, okay, so Y12 into V2 minus V1, so okay, V2 minus V1, okay, so plus Y23 into V2 minus V3, V2 minus V3. And here, what is there? Another offline charging admittance also are there. So there you need to take Y23 dash into V2, Y23 dash into V2. Okay, so this formulation, similarly, that is equal to I2. So for the simplifying, we can take V1 into minus V1 into Y12 V2 into, then whatever the terms is there, that you need to take minus V3 into Y3, that is need to equal to I2. So similarly, node 3. So here spelling mistake, node 3. So node 3. Okay. So here similarly, you need to frame. How to frame? So node 3. Yeah. Node 3 is, so here, what is there? Y13. Okay. First self okay, admittance. That is YD3. YD3 into V3. YD3 into V3 plus. Okay, so here what next? Y3 not into V3. So here also another one, okay, self admittance is there. So that also Y3 not into V3 plus here Y13 where, yeah, Y13 into V3 minus V1. V3 minus V1. Next, offline charging admittance is there. Y13 dash into V3. Okay, so Y13 dash into V3. Next, Y23. Yeah, Y23 into V3 minus V2. Y23 into V3 minus V2. Next, offline charging admittance. Y23 into V3. Y23 into V3. That is equal to 0. So here no current I3 because that is the load bus. Okay. So further simplifying. So you can get okay, we are taking V1 aside and V2 aside and V3 aside. That is equivalent to 0. So rewriting all these three in the matrix format. Matrix format, that is node 1 here. So here always, okay, you need to write like a 1, 2, 3, that is node 1, 2, 3. Here also node 1, 2, 3. Next, V1, we are taking it outside. Okay, so V1, we are taking it outside, means what all the quantities coming in V1. So here V1, so this formulation you need to write here. Okay, next V1, so minus of Y1, 2. Next 3, 3 is, where is 3? Yeah, yeah, here 3 is minus of Y1. So similarly V2. So V2 we are taking it to outside. So V2 means, so here what is V2 here? So V2 is minus 1, 1, 2, minus 1. Next, what is V2? Yeah, here this whole thing we need to take. So VG2, VY1, VY23, Y23 plus Y23 dash. Next, V3, sorry, here again V2. V2 is minus 2, 3 there. Next, V3 where it is. So V3 is, so first from the first node is minus 1, 3. From the second node, it is V2 is, sorry, V3 is minus 2, 3. And here, third node, here what all the terms is that you need to write. So into, that is equal to I1, I2, and Z. Okay, so next, here y1 here in generalized term. In generalized term, this is nothing but y11. This is y12, y13, y21, y22, y23, y31, y32, y33. So into v1, v2, v3, that is equal to i1, i2, and 0. Okay, so where yii is nothing but yii is nothing but equal to sum of the admittance of all the elements connected to the ith node. Okay, so what are all the things connected to the ith node? That is nothing but yii. That is yii is nothing but y11, y22, y3. Okay, next yij. What is yij? Yij is nothing but this terms. Okay, so that is y ij is equal to negative of sum of admittance of all the elements connected between the nodes I and j. So y negative, you know. So in this formulation, this diagonal elements alone positive, and all off diagonal elements are negative. So that is default. So it is coming like negative. That is why ij is equal to negative of sum of the admittance of all the elements connected between the node I and j. That you need to remember. Next, y ij is equal to 0 if there is no line between the bus I and j. If there is no line, then obviously it is 0. Okay, so no line between the bus I and j. Obviously, it will be 0. So that you need to remember. Okay, okay. So while solving the problem, we'll see it clearly. Okay. So as of now, this is the thing. Next, yeah, from the current equation is I is nothing but summation j is equal to 1 to n yij into bj. Already we formulated in the first itself where I is equal to 1 to n. If it is not ij, that is I is not is equal to j, that is yij is equal to ii divided by bj. For all b is equal to 0 except bj. That is short circuit transfer admittance or mutual admittance between I and j. Okay, next yii is equal to ii divided by va. That is va is equal to ii divided by yi, or otherwise in other terms ii is equal to yii into va. Okay, for all b is equal to 0 except va. That is okay, so this is a general formulation. These are the some of the hints you should remember. Okay, next short circuit driving point or self-admittance of the ith bus, that is yi. So next Ybus is nothing but n into n matrix, where n is nothing but number of buses. As I said, say for example I is equal to 3. Okay, so n is also 3. Okay, so that is the hints you need to remember. Then the diagonal elements of Ybus are the driving point admittance, and the off diagonal elements of the Ybus are the short circuit transfer admittance. Okay, so yij is equal to, that is I is not equal to j is equal to 0 if I and j's but are not connected. I and j's but are not connected, then obviously it will be 0. Say for example, in some problems, while solving the problems, I'll tell you. So no connections will be there, then obviously it is 0. Okay, so if the bus is not connected from I to J, okay, so that is, say for example, 3 bus or 4 bus you are taking. So 1 is not connected to 4, then it will be 0. If all the buses connected, then some values will come. Okay, then Y bus admittance matrix is symmetric matrix, that is Yij is equal to Yji if the regulating transformer is not involved. Okay, so say for example, all these values are same, y1 minus y12, and that is equal to minus y1. So here minus y13, that is equal to minus y13 or 3. Here minus 23 is equal to minus 23 or minus 32. Okay, next minus similarly minus 13 is y minus 12 is equal to minus 21. That is all are same. Okay, so that is what given here. Okay, that is what given here. That is Ybus matrix is a symmetric matrix. That is Yij is equal to Yji if the regulating transform is not. Next, by bus admittance matrix is symmetric along the leading diagonal. Okay, we need to store the upper triangle admittance matrix only. If it is symmetric matrix, we need to store the upper triangle matrix. Each that you need to remember. each bus is connected to only few nearby buses. So off-diagonal elements are zero. In such a matrix is called sparse. See, wherever you are keeping it zero, that is wherever the connection is not there in the off-diagonal elements, okay, that you need to mark it as zero. Such matrix is called sparse matrix. This is very, very important. 2 mark question. What is sparse matrix? Sparse matrix is nothing but if, say, for example, each bus is connected to few nearby matrix, that some values will come. If you take the off-diagonal matrix, like say, for example, here, this is the off-diagonal matrix. So this is the diagonal matrix. Okay, say for example, this is the diagonal matrix. Y11, Y22, Y3, they are diagonal matrix. Off-diagonal matrix is nothing but this Y12, Y13, Y23, Y31, Y32 are the off-diagonal matrix. So suppose if the connection is not there, so here Y13 you are keeping as 0. If the connection is not there, Y31 we are connecting as 0, we are putting as 0. So like that, if it is 3 bus, okay, it is very simple. If it is, say for example, 5 cross 5 matrix or 10 cross 10 matrix, so many connections will not be there. So there we need to take it as 0 like that. So Y13 0, Y14 0, or some values. Then say Y15 is 0, Y17 is 0, Y10 10 is also 0, Y10 is 0. Like that, many zeros are happening. That is called the sparse matrix. Okay, so very, very important 2 mark question. So each bus is connected to, so you need to write with that example. Okay, so if you simply like each bus is connected to few names, so many off-diagonal elements are 0. In such matrix called sparse means they will give you only half mark or 1 mark. So if you write with a one example, okay, as I said, so what you need to do is you need to formulate this matrix. You can tell like you can go for some 5 cross 5 matrix, Y11, Y12, Y13, Y14, Y1. So here you can in the next step the problem you can you can take a simple bus system. So 5 cross 5 matrix or 4 cross 4 matrix. So some connection you voluntarily you leave, so that connection will come 0. So you can go for some 0, 0 like that. So if you go for more zeros, that is in the off-diagonal elements, that is called 0. Okay, so that is called the sparse. So like that you need to explain. So that's 2 marks, full 2 marks you will get. Okay, next applications of this Ybus formulation. So Ybus is used in solving the load flow problems. Ybus is used in solving the load flow problems. As I said before, it gained applications owing to its simplicity in data preparation. So if you go for this kind of Ybus formulation, the data preparation is very, very simple. As I said, very easily you can frame up to 10 cross 10 matrix also. Okay, if the impedance values are simple, then very easily you can. So data preparation is very easy. Okay, it can be easily formed and modified for any changes in the network. Say, for example, modified for any changes in the network. Say for example, suppose 10 to 1 is having one connection. You are giving the connection from 10 bus to 1 bus. Okay, like so easily you can modify the matrix also. Simply you go for a Y10 and here 10 cross 10 matrix. Here also 10. So easily you can change. Whereas the thing is that simplicity, you can modify easily in the network if the anything is found newly. So that is the major application. Okay, it reduced the computer memory and time requirement because of the sparse matrix. Say, for example, sparse matrix, many things are 0, so memory also will be reduced, and time for calculation that sparse matrix also that will be very less. Okay, these are the applications of the Ybus formulation matrix. This is also 2 mark question. Okay, applications of Ybus formulation matrix.